Okay, we're going to start talking about exponential functions. Exponential functions have the variable in the exponent, so we're going to learn what they are, learn how to graph them, and look at a few application problems, not as many as you have in your homework, but pay attention to where the exponent is, and you'll substitute whatever value you need in for the x or the variable. Exponential functions can be evaluated with a calculator. Suppose I have f of negative 2 and my basic function is 5 to the x. Well, I say that's 5 to the negative 2 power. Now, a negative power you put on the opposite side of the fraction line, and the negative goes out of the exponent. So a negative 2 just means that 5 squared would be in the denominator, so it's 1 over 25. If you want to enter it in your calculator, you enter 5 and the little carrot top, or what I call a hat, negative 2, and then enter. And then you can change it back to a fraction. And I have some error here in my typing, but anyway, you can change it back to a fraction, and you do that in a couple ways depending on your calculator. On the graphing calculator, you go to the math menu and there'll be a fraction or a decimal key, and then you can play with that to find out which way to go. Another example is 27 to the x power, and you want f to the 2/3. Now, 2/3 really means that you square it and then take the cube root. 1/3 power is the cube root. So you can do it a couple ways, or you could take the cube root of 27, which is 3, and then square it, and that's 9. Or 27 squared, which is 729, and take the cube root of that. Same thing. Or you can put it in your calculator. 27, now always put a fraction in parentheses to the 2/3 power and hit enter, and you'll get 9. If it's a fraction, you need to put it back. If it's a decimal number, you need to put it back as a fraction. Now we have an exponential function. What is an exponential function? You've got some base raised to x power. So again, x is the variable and x is in the exponent. So here your basic exponential function is b to the x. The base has to be greater than 0, and b cannot equal 1. Okay? The domain, set of all real numbers. Range is set of all positive real numbers. The reason b can't be 1 is because that's a straight line. Anything 1 to any power is still 1. So the basic function has an x-axis for a horizontal asymptote and looks like this. Okay? So that's your basic exponential function. This is 3 to the x. Okay? Now, looking at the y-intercept. The y-intercept is always 0, 1 for an exponential function that has not been translated up or down or left or right. The reason being, when x is 0, anything to the 0 power is 1. So that's one point you can always know on an exponential function. Also has a horizontal asymptote at y equals 0, which is the x-axis. Okay, and then it passes through 1b, so b is your base, so in this case 1, 3, and negative 1, 1 over b, or negative 1, 1/3. So those 3 points you can always know for an exponential function are 1 and whatever your base is, if for your y, negative 1 and 1 over your base, and 0, 1. And that gives you an idea of your curve, and it's a pretty quick and easy way to graph an exponential function. Looking at this one, 2 to the x, if you'll notice again, you have 0, 1 as a point, same horizontal asymptote, passes through 1, 2 in this case because my base is 2, and negative 1 and 1/2 because my base is 2. Now, exponential functions can transform up, down, left, right, just like our quadratics and our linears or any other common function. So let's look at this one. It's been reflected around the y-axis. We've done that by making the exponent negative. 3 to the negative x causes this reflection. Okay. Here's another one. This one, if you look, it's moved to the left and it's moved down 1 from where it was. Now, one way to look at it is where it moves from that 0, 1 point. Okay? Where is it? It's moved to the left 2 spaces and down 1 space. So, left, remember, is grouped in with the x, so that's in with the exponent is x plus 2. That caused it left 2. Again, those left and right moves seem a little backwards. Plus is left, minus would be right. And then the minus 1, the vertical translation means it goes down 1 unit. Now these are a few application problems. I focus mostly on interest problems because those are ones you'll use or potentially will at least need to use in real life. In these, the symbols stand for principal. That's the amount you invest or originally have. R is your interest rate, and it's always a percent, so in the problem, be sure you divide it by 100 instead of leaving with the percentage. N is however many compounds you have in a year. You remember, sometimes you'll hear something's compounded monthly or quarterly. Monthly is 12 compounds a year, quarterly is 4 compounds a year, annually is 1. T is the number of years, and A is the amount you end up after your investment is complete. So, an example. We want to charge $769.41 for a washing machine at 3.95% interest for 10.5 years. How much does it really cost us if we compound the interest twice a year? So, there we have it. We put our P, that's the amount we originally invest, 1 plus 0.0395 over 2, that's the number of compounds, times 2, which is the number of compounds again, times 10.5 years. Put that in our calculator and get an answer. Here you want a couple wishes to retire 14 years from now. That spelling is really good. N-O-W. With $1 million, how much must they invest now at 6.4% compounded monthly to reach this goal? So, you're going to set up your problem. In this case, 1,000 is what they want to have at the end, so that's our A, and we have to figure out our P. Interest, again, divided by 100. Compounded monthly means there's 12 compounds, so that's the denominator there and also up in your exponent for 14 years. Okay. Now we can go ahead and evaluate the 1.0053 to the 168th power in our calculator and get a number. Then you divide 1 million by that to solve for P, and that tells me how much they would have to invest to end up with $1 million at the end of 14 years. Now, so a lot of times here we're going to use a base E. E is an actual number, just like pi represents a number. E represents a number, and it is 2.71828 and goes on and on and on, just like pi does. Now, you should have on your calculators an E button, but if you don't, just use this number, and you'll get close enough. But a lot of times it's found over the LN button on your calculator. And you'll have e to some power. Exponential functions with a base e look just like the graphs you've learned because it's a number, and so they can be translated the same way. E is used for many applications: continuous interest, carbon dating, a lot of natural, that's why it's called a natural log later when we take log. A lot of naturally occurring phenomena end up with a base of E as part of their calculation. Continuous interest is different than compound interest. Again, though, the A and P stand for the same thing: principal and the amount you want to have at the end of the investment. R is your interest rate. T is the number of years. There's just not a number of compounds in this formula because it's compounded continuously. Okay, so this is the formula for that. Now here's an example. How much money should be deposited into a money account that pays 5% a year compounded continuously to have $38,000 in the account in 20 years? So there's our formula. Remember, divide by 100 for your interest, 20 years. Okay, now 20 times 0.05 is 1, so we just have e's. And so 38,000 divided by e, which is again 2.78, whatever, gives me this amount at the end that we need to invest. Now here's a mistake in this one. Let's see if you can figure out what it is. We've got $15,000 invested at 3% interest. How much in the account in 6 months? So we've set it up. Study that for just a second and tell me if you can figure out where the mistake is. Okay. Hopefully you caught it, because this is a common mistake that people make. T is the number of years, and so instead of 6 months, you should use 0.5 years. So remember that T will always be in years. If that's something, notice through time and be sure that you've changed it to years. So this is what the problem should have actually looked like, and the amount is significantly different than if we use the 6.